Hi everyone, I'm Frank. Today I will present White-Boxing RDMA with Packet-Granular software control. This is a joint work with Jaehong, Ming Liu, and my advisor Arvind. We are from University of Washington and University of Wisconsin-Madison. RDMA is popular. Numerous ideas are emerging to customize RDMA transport, including congestion control, multi-tenant isolation, routing, and more innovations. There are several driving forces behind them. Firstly, it is driven by workload. RDMA empowers data center workload, such as disaggregated storage, HPC, and GPU communication. Also, it is driven by large-scale deployment. For instance, error report using RDMA to support large-scale storage workload. For adapting to diverse workload and deployment, there are several ideas to customize RDMA from both academia and industrial. For example, last 5 years, more than 30 NSDI and SICOM papers explore RDMA innovations. Our community is so smart. We have a bunch of new ideas. Question is that how to landing new ideas into RDMA NIC. However, it is not trivial to implement new customizations into RDMA NIC. The reason is that RDMA features on hardware transport to achieve high performance. Both control and data logic are fixed into hardware modules like ASIC. Next, we quickly go through the RDMA architecture. On host side, user operate QP to interact with NIC and submit UQI for work request. Due to hardware implementation, most functionalities are running over the NIC side. Within the RDMA NIC, it has two major components. One for control logic, such as QP scheduler. Another one is transport unit, such as Rocky V2 or InfiniBand. The control logic keeps track of some QP context and UQI cache to generate execution order for transport unit. Importantly, during the scheduling, QP scheduler also considers the rate assignment from congestion control module. We can see that both control and data logic are fixed into the ASIC module. So how can we customize? For example, if we want to implement a new congestion control algorithm, we have several methods. Firstly, we can use FPGA to develop a new NIC. As we know, it requires very high development cost. Secondly, we can wait for hardware vendor to deliver next generation of ASIC. It typically takes years. Also, we can use software emulation, such as Software-Rocky. However, it will lose performance. Performance is a key benefit of RDMA, so we don't want to trade it off. Ideally, we expect we can customize the control with flexible software. At the same time, we keep the high-performance data logic. In this project, inspired by SDN, we propose white-boxing methodology. Next, we will describe how to realize this vision. Besides the strong motivation for software control, we have another enabler that is programmable NIC. Latest RDMA NICs provide some building blocks for software control. With the same architecture as before, now RDMA NIC is one module of Smart NIC SoC. Then, from high-level understanding, SoC attach one multi-core processor to RDMA NIC. It can program rate assignment module. Notably, these cores are much more lightweight than typical Smart NIC ARM cores. With the embedded processor, we have some building blocks. First one is general computation. We can use software to express control logic. Secondly, it is a read control interface. The processor has APIs to set rate for each QP. Also, now the embedded processor can receive some signals from RDMA NIC. For example, RDMA NICs will report ECM marking to the embedded processor. Although we have Smart NICs providing some beautiful building blocks, we still have some challenges to realize the vision of our white-boxing RDMA. First one is flexibility. We aim to express diverse control actions over the same framework that rely on various control signals and different control laws. How can we use one framework to express most of the control functionalities? Second one is granularity. We aim at supporting fine-grained control. However, for high-speed line rates, packet-granular events are also high-speed. Boosting efficiency is very important. Third challenge is scalability. We need to handle multiple concurrent flows over the same framework. Next, we will introduce our solution, Software-Controlled RDMA SCR framework, to achieve these three goals. Firstly, we address the flexibility, how to support diverse policies. The key idea is that we repurpose the rate assignment for DQ rate control. Revisit the RDMA NIC architecture. Now, with the embedded processor, the rate assignment module is programmable. Previously, it is a fabric congestion control that determines the rate assignment. However, there are several cases which are not handled by the congestion control. For example, for multi-tenant isolation, congestion control is not sufficient. We have 2 QPs for 100G network. One QP takes 90 Gbps, other QP takes 10 Gbps, which is not fair. However, the total bandwidth is 100G, and no congestion happens in network, so the congestion control module will not take actions to do this. Actually, this rate assignment knob is very powerful. We can encode much more information into the rate assignment, go beyond the congestion control. We repurpose the rate assignment for DQ rate control. What is DQ rate? DQ rate is the speed for RDMA NICs to fetch message from host memory regions. Next, we will introduce why DQ rate is more comprehensive as a control model. Compared with the typical congestion control, the DQ rate influences multiple aspects of RDMA transport. We consider general setting, including local host, fabric, and peer receiver. For host domains, the DQ rate determines resource allocation within RDMA NIC architecture. For fabric domains, it impacts the sending rate, as message can only be sent out after we DQ from the host region. For peer domain, the DQ rate can respond to back pressure signals from the receiver side. Overall, the DQ rate provides a comprehensive control. For SCR, details about event list and the collection method are in our paper. Next challenge is granularity, how to control at packet level. It is not trivial. Consider 100G line range and a typical MTU size. For this setting, each packet granular event is sub-microsecond as low as 120 nanosecond. It is very tight budget for software over general purpose processor. To handle this high-speed line rate, we have a workflow with queuing. We have RDMA NIC datapath and software control framework. Firstly, we have 3 collectors to receive event from different domains as we described before. After event collection, we store events in a queuing system before processing. Then we use multiplexer to invoke multi-core processor to handle events and output control actions. Queuing typically has delay, but it doesn't matter if we can coalesce them. Next, we will introduce how to utilize such queuing system. The event queue system is to facilitate event coalescing. It is a crucial mechanism for managing high-speed packet granular events. We explain the coalescing mechanism using a TX event. In RDMA operation, each UQUI can indicate a large message size, up to gigabytes. Generally, users configure large queue depths to enable batching. Going through the TX pipe, a message with a single UQUI could be segmented into a large number of MTU-sized packets because the network has a typically small MTU. So gigabyte message could be segmented into a large number of packets. Each packet has one signal for TX event queue. So coalescing multiple consecutive events into one is a promising solution to improve processing efficiency. To support a diverse event, we design software and hardware hybrid coalescing. Firstly, NIC provides hardware coalescing, but not all domains have the hardware modules. For example, host domain collector is software-driven, so we need software modules to do that. Moreover, software modules enable the programmability of coalescing strategy. We can customize suitable policies for different signals. For example, for the RTT event, we can just keep the latest one and drop others. Third challenge is about scalability, how to control many flows at the same time. Intuitively, increasing the number of flows, it seems that we have to compromise the granularity. Actually, it is not always true. Next, we will present one simple yet effective observations. Adding more flows doesn't hurt per flow coalescing granularity. Here, granularity means that how many packets are coalesced into one event. Here, we illustrated the observation. For the simple case, we have one QP and 2 threads reserved for processing. We assume that event processing rate is stable for each thread. Here, given the stable processing rate, we assume 4 packets are coalesced into one, so the granularity is 4. Now we have 2 flows. 2 flows share the same line rate. Each flow is processed by one thread. Compared with the previous case, the event processing rate is the same, but the coming rate for each flow is halving. Then the granularity is better, just 2, more fine-grained. Now we increase to the 4 flows. Now the flow number is more than the number of threads. 2 flows will share the same processing rate. Although we have more flows for each thread, the coming rate is still be the same as the previous case, so the granularity is still 2. We call it the granularity invariance. Principle is simple. Because line rate is invariant, if we can catch up with line rate, good, we are done to match how many flows will increase. The granularity invariance principle provides scalability guarantees for per flow processing. After addressing all challenges, we have the software-controlled RDMA framework that is the complete workflow. On implementation, we prototype the system over BlueField-3. Specifically, we use the Datapath Accelerator DPA. DPA is a RISC-V-based embedded course. It supports heavy multi-threading. It applies very lightweight RTOS. Also, it is low-cost hardware with limited cache and memory system. DPA is low-profile embedded processor. To further improve performance, we take the run-to-completion model and improve cache performance, and we overcome some RTOS constraints, such as lacking the runtime support for thread management. BF3 and DPA are new hardware, so please check our paper for detailed characterization and implementation. SCR is a framework. For white-boxing methodology, flexibility is a key benefit. Next, we demonstrate how to enable new functionalities over SCR. To comprehensively cover a wide range of innovations, we categorize them into various system domains, as before. Also, we use SCR for GPU-Direct and NVMe-oF RDMA with 0 modifications. We enable a spectrum of new customization here. In this presentation, we focus on one case, the fair QP scheduler. For the case of fair QP scheduler, we investigate the problem of bandwidth allocation. We assume several tenants. They set up QP and varying message size. We consider 2 metrics. One is fairness, and another one is utilization. SCR can express lots of algorithms. Here we show 3 typical ones. First one is the default RDMA NIC scheduler. For default one, it can achieve high utilization, but large-sized QP will typically grab most of bandwidth, which incurs starvation for small-sized QP. Later, we will show experiment. It will hurt the performance of small message QP, and for example, it will increase the latency for small message. Second one is static allocation. We statically and equally control the decay rate for each flow. This is very fair, but it will lead to over-provisioning for small-sized QP, and it will waste the bandwidth. Third one is water filling strategy, which is more dynamic and on-demand. At the starting time, we have remaining bandwidth. All flows get 0 allocations. Next, we fill the demand for each flows with a small amount. If 0 is saturated, for example, for small flows, we stop filling. For other flows, we continue to fill until they are saturated. For second round, middle QP is done. Finally, we run out of bandwidth and stop the water filling procedure. Next, we will show experiment for these 3 typical examples. Over a real hardware testbed, we run end-to-end tests with 2 QPs. X-axis is one flow, Y-axis is another flow, and we have 2 metrics. Deeper green is more fair, deeper blue is higher utilizations. We can see that water filling is more fair and achieve high utilizations. Actually, compared with algorithm optimality, we highlight the flexibility and expressiveness of our framework. Besides enabling new algorithm, SCR can support fine-tuning one specific algorithm, for example, water filling. Water filling has a bunch of design knobs. Here we consider one design choice. How can we reset existing flow when a new flow joins? Here we dump out the trees from real workload. X-axis is timeline, Y-axis is decay rate, and each color represents one flow. For this trace, we take a straightforward strategy, which is a heuristic and stateless. When a new flow joins, the first design question is that how to scale down the decay rate of an existing flow. For this trace, we scale down to half. Next design question is how we can start new flows. Here we start from 0. We can say that the problem for this strategy is that it converges slowly and not fair. Let's further improve the strategy. Because SCR can track state, for example, the number of active flows. Utilizing this state, we can design better algorithms. For second trace, we scale down to n-1 over n, and we start new flow from 1 over n. For this strategy, it can quickly converge and remain fairness. The takeaway for this test is that SCR can enable fine-tuning and customization for specific algorithms. In this paper, we demonstrate more use cases. For first case of QP scheduler, we support GPU-Direct and NVMe over Fabric. For second case, we try RTT-based congestion control for RDMA. For third case of pure domain, we enable the receiver-driven flow control. For the Fabric domain, we enable multi-pass monitoring to help make routing decisions. Please check more details in the paper. To summarize, in this project, we advocate for White-Boxing RDMA methodology. Accordingly, we design SCR framework to achieve flexibility, fine-grained control, and scalability. Finally, we envision SCR can help landing new customization for RDMA transport. Thanks for listening, and I'm happy to take questions.